Now, in this video, we're going to talk about a property of elements, electronegativity. A property that describes the ability of an atom, or more rarely a functional group, to attract electron density towards itself in a chemical bond. But we're going to focus on how electronegativity values can be used to predict bond types, and doing a few exercises which would involve putting a group of elements either in their order of increasing or decreasing electronegativity values. Generally, when the difference in the electronegativity values of the bonding atoms is less than 0.5, then we have a non-polar covalent bond. However, when the difference in the electronegativity values is greater than 0.5 but less than 1.7, then we have a polar covalent bond. And when the difference in the electronegativity values of the bonding atoms is greater than 1.7, we have an ionic bond on hand. Now, the electronegativity value of chlorine is 3.16. That of hydrogen is 2.20. Carbon is 2.55. Oxygen is 3.44. Now, fluorine has 3.98 for electronegativity value. So we're going to compare the electronegativity values of the bonding atoms and determine their differences and compare to the options, the three options that we have, and just use that to predict the bond type. Now, we have a chlorine to chlorine bond, which is a molecule involving the same atoms. So we have a difference in their electronegativity values as 0. So we have a non-polar covalent bond for a chlorine to chlorine bond, and it so applies to all diatomics when it involves the same atom having the same electronegativity value. Carbon has an EN value of 2.55, hydrogen is 2.20, and so we have an electronegativity value difference of 0.35, and that makes carbon to hydrogen bond also a non-polar covalent bond. Oxygen is 3.44, hydrogen is 2.20, so we have a difference of 1.24, and that makes the hydrogen-oxygen bond a polar covalent bond. And here, what it means is that when oxygen goes into a bond with hydrogen, because of its high electronegativity value compared to hydrogen, the bonding electrons will be attracted more towards the oxygen than towards the hydrogen. And it's going to make the oxygen end of this molecule partially negative and the hydrogen end of this molecule partially positive. Hydrogen fluoride. Hydrogen has an EN value of 2.20. Fluorine is 3.98. They have an EN value difference of 1.78, which falls within the third option and makes the hydrogen fluoride bond an ionic bond. Here it means that the electronegativity value of fluorine is so high that when it goes into a bond with hydrogen with a comparatively low electronegativity value, it's going to involve the transfer of an electron towards the fluorine. You know, fluorine has 7 electrons in the valence shell. It would require just one more electron in order to assume the noble gas electron configuration. So it has a very strong attraction for electrons. It completely takes over the bonding electrons. In fact, it steals the bonding electrons. And so hydrogen fluoride bond is an ionic bond. Now, hydrogen chlorine has an electronegativity value because hydrogen is 2.20, chlorine is 3.16. The difference in their electronegativity value is 0.96, which falls within the second option greater than 0.5, less than 1.7, it makes hydrogen chloride bond a polar covalent bond. And here also it means that the hydrogen end of this molecule becomes partially positive and the chlorine end of this molecule becomes partially negative. And so the difference in the electronegativity values of the bonding atoms is very important to determine the bond types existing within the molecule. The electron configuration of the bonding atoms plays also a role to determine the bond types and also the orbital shield of the elements involved in the bond. But it is important to note that the difference in the electronegativity values of the bonding atoms is very crucial in determining the bond types within molecules. Now, for question 5, 6, and 7, we are expected to put these set of elements in their order of increasing electronegativity values. Sorry, this is 0.35. Question 5, oxygen, lithium, arsenic, and selenium. Let's go ahead and locate these elements on the periodic table. So we have oxygen, arsenic, selenium, and lithium. Generally, the electronegativity values of elements increases from left to right on the periodic table and up the group. Now, for these set of elements, lithium is far to the left of the periodic table. Now, arsenic is to the left of selenium, so arsenic would have a lower electronegativity value compared to selenium. And there are 2 steps below oxygen. Although arsenic and selenium are 2 steps below lithium in the period, lithium is far to the left on the periodic table. And so we're going to put the order as lithium, arsenic, selenium, and oxygen. Lithium, arsenic, selenium, and oxygen. Now, if we were to be asked to put them in order of decreasing electronegativity value, then the opposite order would have been the case. And so this is in the order of increasing electronegativity value. Now, if we were asked to put them in order of decreasing electronegativity value, then the order would have been oxygen, selenium, arsenic, lithium. Now, for arsenic, barium, iodine, lead, boron, and lithium, let's attempt to locate them on the periodic table. So we have arsenic here, barium, lead here, iodine, boron in the second row, and lithium here. Now, barium and lead are in the 6th period. Iodine is a halogen. The halogens generally have very high electronegativity values compared to the metals, which are far to the left. Now, lithium is to the left of boron, so lithium is definitely going to have a lower EN value compared to boron. Arsenic is in the 4th period. Generally, the electronegativity values increases from left to right and up the group. And so I'm going to put the order as barium, lead, arsenic, lithium, boron, and iodine. So I'm going to put the order of increasing electronegativity value as barium, lead, Now, if we were asked to put them in order of decreasing electronegativity value, then the opposite order would have been the case. Now, we have chlorine, potassium, sulfur, calcium, and oxygen. Let's locate them on the periodic table. we have chlorine, potassium, calcium, sulfur, and oxygen. Now, sulfur is to the left of chlorine. So definitely sulfur is going to have a lower EN value compared to chlorine, and it's going to have a lower EN value compared to oxygen because it is one step lower oxygen. Now, electronegativity values increases up the group. And so we're expecting sulfur to have a lower EN value compared to oxygen and also lower compared to chlorine. Calcium and potassium are far to the left, and so we're going to have calcium and potassium definitely having the lowest electronegativity values, but potassium is to the left of calcium, so we're going to put the order as potassium, calcium, sulfur, chlorine, and oxygen. Potassium, calcium, sulfur, chlorine, and oxygen. And if we were to be asked to put them in a decreasing order of electronegativity value, the opposite would have been the case as oxygen, chlorine, sulfur, calcium, and potassium. Now, with question 8, for ions of the same element, the more positively charged the ion, the higher the electronegativity values. Generally, cations are smaller than their parent neutral atom because they have fewer electrons, and the remaining electrons are held more tightly by the nucleus. Now, sodium is the 11th element on the periodic table. Sodium cation 1 plus has lost 1 electron, so we are left with 10 electrons here. We are left with 9 electrons, 8 electrons, and we have 11 electrons. So the fewer the number of electrons, the greater the nuclear influence on them. The more tightly they are held by the nucleus, and the greater its electronegativity value. Now, we should also remember that sodium is group 1 on the periodic table. It has 1 valence shell electron, and it would prefer to lose that valence shell electron and assume or obtain the noble gas electron configuration and become stable. And so it wouldn't desire to gain an electron. If you compare that to sodium cation 1 plus, it has lost 1 electron and obtained the noble gas electron configuration, and it would also not desire to gain an electron. But in relative terms, if I'm to have an electron in the space of sodium cation, one would expect that the unlike charges are going to attract each other, and we would expect that the more positively charged the cation, the stronger the attraction for an electron would be. So I'm going to put the order as so that will be the order of increasing electronegativity value. And this applies for cations of the same element, because it would have been different if we were to be comparing sodium cation and fluorine. Fluorine is very electronegative and even more electronegative than sodium cation 1 plus. And so we should be very careful which elements we are comparing. But generally, for cations of the same element, the more positively charged the ion, the higher its electronegativity value. Now, for anions, the opposite is the case. Generally, anions are bigger than their parent atom because it has acquired extra electrons. And the more electrons it acquires, the greater its size becomes, and the lesser the nuclear influence on the extra electrons. Now, if I'm to put an electron in the space of fluorine anion, the negatively charged particles are going to repel each other, and the more negatively charged the anion, the greater the repulsion here is going to be. And so for anions of the same element, the more negatively charged the anion, the lower its electronegativity value. So I'm going to put the order as this. So this is the order of increasing electronegativity value. Now, for question 10, we're looking at atoms with hybridized orbitals. We may be familiar with different types of hybridized orbitals, but for the purposes of this question, we will be focusing on the sp hybridized orbital, sp2, and the sp3 hybridized orbitals. Now, generally, for atom with hybridized orbitals, the more the s character a hybridized orbital has, the more strongly it would attract bonding electrons. So it means that the electron attracting tendency of the hybridized orbital of the atom is based on the amount of the s character. And so when we consider these three bonds, for example, for carbon, which has undergone different types of hybridization, the carbon in the carbon to carbon single bond has undergone sp3 hybridization. The double bond carbon has undergone sp2 hybridization, and the carbon in the triple bond has undergone sp hybridization. So it means that the carbon here in the single bond is sp3 hybridized. In the double bond, the carbon is sp2 hybridized, and the carbon in this triple bond is sp hybridized. Now it means that here the s orbital has a 25% character. In the sp2, the s orbital has a 33.33% character, and in the sp, this hybridized orbital has a 50% s character, and the p character is 75%. For the sp3, 66 for the sp2, and 50% for the sp hybridized orbital. So the s character in the sp hybridized orbital of the carbon atom is more than the carbon in the double bond, and also more than the carbon in the single bond. And the reason is that the s orbitals are very spherical. They have better penetration effect, and that means that they are closer to the nucleus than the p orbitals. And so the nucleus is able to keep hold of the electrons more firmly and more tightly to itself, and ready to accept extra electrons too. So the carbon in the triple bond would have a stronger attraction for extra electrons than the carbon in the double bond, then lastly than the carbon in the single bond. So I'm going to put the order of increasing electronegativity as so that is the order of increasing electronegativity values. And if we were to be asked to put them in order of decreasing electronegativity values, the opposite would have been the case. The order would have been this. So this would have been in the order of increasing electronegativity value, and this order of decreasing electronegativity value. So this is the end of my video. Thank you very much for watching, but keep watching.